Continuing on with vector calculus, last episode we looked at differentiating vectors, now we're looking at integrating vectors. So if you recall from just integration in general, if you integrate a function, you need to have a constant of integration. Because it's taking the gradient and then finding the original function, that doesn't tell us what the vertical translation is. So we need some sort of extra information to tell us where it sits on the plane. In our case, we call that vector c. And we have this relationship between acceleration, velocity, and position vector. Because they're derivatives of each other, we can also use integration to find the other components from going from acceleration to velocity, etc. So velocity is just the integral of acceleration with respect to time, and position is the integral of velocity with respect to time. So looking at that, for example 8, we have an acceleration vector of a moving particle given by cosine of t on 2, I minus sine of t on 2, j, and we're given a t-bound of 0 to 4 pi. We're told that the initial velocity, so that's v of 0, is equal to 2j. So that's going to be useful information for us to find the constant of integration going from acceleration to velocity. And then we're also given the initial position, so that's r of 0 is equal to I take 3j. So that's going to be useful to find the constant of integration going from velocity to position. And we're asked to determine the Cartesian equation of the path. So we're starting with acceleration, which, just a reminder, is the second derivative of position with respect to time. So that is cosine of t on 2, I, and then minus sine t on 2j. So that gives us r of t is equal to the integral of the x component minus the integral of the y component. And so that gives us 1/2. So because we're getting from the original function, we're anti-deriving it, so that t on 2 would have halved it, so we need to multiply it by 2, so it's going to be 2 times sine t on 2i. So we can see if I were to differentiate that, I'd have to also differentiate the what's in the sine, so that's just chain rule applying there. So when I drop that a half out the front, we need to go back to cosine of t on 2, so that half needs to cancel out with the 2. So that gives us our I component, and then our x component. We've got negative sign. When we integrate that, we're going to go back to positive, so that's going to be 2 cosine t on 2 j. But then we also have our constant vector. So to find the value of our constant vector, let's call it c1, because we know we're going to have a second one later. We want to substitute in the information we have up here. So we know that r dot of 0 is equal to 2j. So we know that sine of 0 is going to give us 0 in the I component, and then cos of 0 is going to give us 1 in the j component. So we can see that in this case, c will be 0, because we're going to have 2j is equal to 2 cosine 0j plus c. Therefore, c1 is equal to 0. So then, moving on to find the position, we have to integrate it again. So r of t is equal to the integral of r dot of t, which means we're integrating 2 sine 2 on t I. Sorry, let's get our dt in there. Plus the integral of 2 cosine t on 2. So that was supposed to be t on 2, sorry. dtj. That is going to give us negative 4 cosine t onto I plus 4 sine t onto j. And that's going to be our r of t. So we know that r of 0 is equal to I minus 3j. Therefore, so we had our plus c here. We've got that negative 4 cosine of 0 plus I plus c plus 4 sine of 0 j minus 3j is going to have to equal 0. So if we find all this and we get c, let's call it c2, over to the left-hand side, we find that c2 is equal to 5i minus 3j. All right, so the only way for that to cancel out is we need to have that minus 3j and that 5i there. So that comes from negative 4 cosine of 0, giving us negative 4 times 1, and then 4 sine 0 is going to be 4 times 0. So then taking the negative 5i and the positive 3j to the other side. Yeah. So moving on from that, that gives us our C2. So that gives us our R of t, which is equal to negative 4 cosine t onto plus 5 I. And then we also have plus 4 sine t onto minus 3j. And we want to turn this into a Cartesian equation. So what we're going to do is just let x equal negative 4 cosine t onto plus 5 and y equal positive 4 sine t onto minus 3. And then all we want to do here is make cos of t the subject. So we're going to get x minus 5 on negative 4 equals cos of t on 2. And then y plus 3 on 4 equals sine of t on 2. And then now that we've got cosine and sine, we can use the Pythagorean identity, add the squares, and that's going to equal to 1. So therefore, 1 is going to be equal to x minus 5 squared. Negative 4 becomes positive 16 when it's squared. And then plus y plus 3 squared, also on 16. So we can see that this is a circle with center 5, negative 3. And it's going to have a radius of 4. So multiplying each term by 16 gets the 16 onto the left-hand side. So this is 16 equals x sec 5 squared plus y plus 3 squared. Okay, and that's everything for this video, shorter one for today. Thank you.